All right, ladies and gentlemen, lesson 9.2, we're going to deal with the Pythagorean theorem. Maybe you've heard of this theorem before. Possibly not, but we're going to discuss it nonetheless. And so at the end of this particular little lesson, hopefully you're able to use the Pythagorean theorem to solve problems. Now, first thing, let's talk about the Pythagorean theorem as it applies to right triangles, because that's the one thing you have to understand, is that the Pythagorean theorem only applies to right triangles. So if we have any other type of triangle, then the Pythagorean theorem does not apply. Okay, so it only applies to right triangles. Now, in order to deal with the Pythagorean theorem, we have to talk about the parts of a right triangle. So first of all here, and let me go ahead and pull this out, a right triangle has two legs. Okay, and the legs of the right triangle are the sides that include the right angle. So in this particular case here, we have the right angle here. So this side here and this side here, those are both the legs of the right triangle. Then we also have what is called the hypotenuse. Funky word. I'm not even sure where it comes from. Probably some Greek thing somewhere way back when. And the hypotenuse in a right triangle is the side that is opposite of the right angle. So it's across from the right angle. Now, one of the key important things about the hypotenuse, it is always the longest of the three sides. Always. So if we're talking about answers that make sense when you're doing a problem here, if your hypotenuse ends up being equal to or shorter than a leg, you have a problem. At that point, you need to go back and figure out what the problem is. So those are the parts. Now, and I'm going to go sort of back and forth between a couple slides here. In your previous, you just did an activity where you had a couple puzzle frames, and you had some puzzle pieces to fit into those frames, and your arrangements should have ended up being something like this, okay, where we had the big square in one of the frames, along with four of the right triangles, and then the two smaller squares fit into the other frame, and also having four triangles involved. Now, so you did the arrangement, you cut them out, you put them in, and so what are the conclusions that we can draw? Okay, well, a couple things that have to come to your mind when we do this, or when we've done this activity, is to realize that first of all, we have four identical right triangles in each of the frames. Okay, so we've got these two and these two, so that's four. We've got these four over here. Those identical triangles in each frame, so the four that are here and the four that are here, are all covering the same amount of area. Okay, so the four, again, these four, these two and two here, these four over here, they're all covering the same amount of space. Okay, so the area that remains has to be the same. Well, this big square over here covers the rest of the remaining area in this frame. These two little squares over here cover the rest of the remaining space in this other frame. So the sum, if I add these two areas together, that has to be the same as this big area here. Why? Because, well, we're covering everything. So even though the orientation is different, this area of the big square here has to be equal to the area of these two little squares put together, because they cover the rest of the remaining space. So what does that tell us? Well, that the areas of the little squares, again, when I take those sums, when I add those together, has to be equal to the big squares. Now, the one other thing that we have to be aware of also, and I hope you noticed that the right triangles, now this is not exactly like the previous slide, but that these squares, the lengths of the sides of the squares happen to fit on the particular right triangles that you have. But anyway, so the areas of the squares on the shorter legs, if I add those together, has to equal the area of the big square. Well, how does that help us? Well, okay. So I have a right triangle here that has legs of 3 units and 2 units. So my legs are 3 and 2. My hypotenuse is an unknown. Okay? And so knowing this relationship amongst areas, the area of this square here, let me get it to pop up, plus the area of this square here, if I add those two things together, has to equal the area of this square over here. So I can use that going through. Now, again, if this is a square, it doesn't look exactly like a square, but this would be 2 by 2. Well, the area of this square then has to be 4. Okay, because 2 times 2 is 4. How do we find the area of the square? Well, length times width. 2 times 2 is 4. This square down here would have to be 3 by 3. Well, 3 times 3 is 9. Well, if I add these two areas together, 9 plus 4, well, that's 13. Okay, so the area of this square up here has to be 13. Well, as we discussed in previous units, if I have the area of this square, if I take its side length, or I'm sorry, I didn't say that right. To get its side length, if I take the square root of that side length, okay, well, what is the square root of 13? And we can go through that whole process. We can either punch it into a calculator if we want to, or if we want to do the whole, finding squares above and squares below, we know that this would be, the square below would be 9, so we would have 3 here. The square root above would be 16, or the perfect square above, sorry, would be 16, so that would be 4. So we're between 3 and 4, so we're at about 3 point, let's see, we're 4 units away here, we're 3 units away there, a little closer, about 3.6. So the length of the hypotenuse here would be approximately 3.6 units. Okay. Now again, answers that make sense. I already told you that the hypotenuse has to be the longest of the 3 sides. Well, is 3.6 longer than 3 and 2? Yes. So, and again though, that could be punched into a calculator and done a little bit more quickly if you so chose to do that. So, just depending on how you want to deal with that problem. So we'll take this one step further. Okay. We're going to actually construct the Pythagorean theorem now. So I know that the area of this square on the leg, well, the length is a. So if I'm going to go a times a, that the area of this square would be a squared. A times a is a squared. Okay. If this length of this leg is b, so this would be another b over here because the sides would be the same length. B times b is b squared. Well, a squared plus b squared is what I would have here. If I add those together, that has to equal the area of this square over here. Well, we know c by c, well, that's c squared. So you get a squared plus b squared, the area of the one leg, plus the area of the other leg, is equal to the area of the third leg. And this, by the way, is the Pythagorean theorem. So let me pop quickly to the next slide here. So the Pythagorean theorem, and this is the long version here, in any right triangle, the sum of the squares of the lengths of the legs is equal to the square of the length of the hypotenuse, which that's the long version. Here's the short version, which we just came up with. A squared plus b squared. These are the legs. The areas of the legs in either order, the order does not matter, is equal to the square, the area of the hypotenuse. So this is a formula that we'll work off of most of the time. Okay. So when we use the Pythagorean theorem, we're going to come back to this little formula. If you can use this formula, it will make your life a whole lot simpler. So let's go ahead and let's find the areas. Let me change colors here of these things. Actually, you know what? Let me do it in green just to, I'll try to keep these in. Okay. So my leg is 2 here. My leg is 2 here. And so my A and my B, those are my legs. So I'm going to put my 2 in, and this will end up being squared, and my 2 in, and this will be squared. And we are, in this case, trying to find, because here my C would be here. That's my hypotenuse. C is considered the hypotenuse, just an organizational thing for us. That's supposed to be a C. So I'm trying to find C. Okay. Well, let's go ahead and raise our powers. 2 squared is 4. 2 squared is 4. That equals my c squared. Okay. 4 plus 4, I'm just simplifying, is 8. All right, that equals c squared. So what that's telling me here is, and I'm not going to go ahead and draw the whole thing, but if I were to draw this square out here, the area of that square would be 8. Well, we don't want the area of that square. We want the side length, so we know we're going to end up square rooting this. So I'm going to take the square root of both sides of this equation, which, by the way, squares and square roots cancel out. So the square root of 8, and I'm just going to round it off to, in this case, I'm just going to go to the nearest tenth, is approximately 2.8 units. And now, again, as we recall, 2.8, the hypotenuse has to be the longest of the 3 sides. In this case, it is, so it works. All right. So that's if we happen to know the 2 legs. In this particular case, though, we're going to go backwards. What if we know the area of the big square, of the hypotenuse, we know the area of one of the legs, we want to find the area of the other leg? Well, in that particular case, we're working backwards. We're going to have to subtract. Okay, so if I know this and I know this, if I subtract the little out of the big, I'm left with the other little. Okay, and this is how it works if you use the formula. So, and this just takes a little practice. Okay, in this case, I'm given 15, in this case to keep it in color-coded. And that is my hypotenuse, so my 15 is going in for C. Okay? My legs, in this case, are 9 and the other. And it does not matter which order. I'm going to just use this for my B. So I'm going to let B be unknown, but you could have used it as A. Those are interchangeable. My 9 is one of my legs, so it has to go in for A or B. Again, those are interchangeable. So here's what happens. We're solving an equation is what we're doing. The first thing is simplify the things that can be simplified. So 9 squared, well, that's 81. Plus my B squared, that's my unknown. I'm going to bring it down. And that equals my 15 squared, which 15 times 15 is 225. Again, let me change my, just trying to keep these somewhat color-coded for right now. Okay. Again, I'm solving this equation, so I'm going to isolate this variable. So I have to get rid of the 81, so I will subtract 81 from both sides of my equation. And I have, whatever I do to one side, I have to do to the other. That's why we did all that solving equation stuff way back when, so that we can keep balance. 225 minus 81 is 144. So what we've actually found here is, again, if I were to draw this, this is not a square, it's just a representation. If I had attached this square out here, the area of this square would be 144. You don't have to put that. I'm just showing you that that's what it would be. Again, I don't want the area. I want the side length. So if I take the square root of this 144, that will tell me how long each side is. So that is what I'm going to do in my equation. I'm going to undo this square with a square root. Whatever I do to one side, I do to the other. The square and the square root cancel out, so I'm left with B. And the square root of 144 is 12. So I know that B in this case is 12. So what we're doing basically is we're working backwards through the problem. In essence, we were sort of given the answer. In this case, we had the 15, and so we were working backwards to one of the legs. So the subtraction method came into play. So, all right, and so now in this particular case, we're going to use find the length of the missing side. Well, in this case, you're going to sort of look at me and sort of think, well, I've got numerous missing sides, which actually I don't. Okay, if this is on what we have here is we have an XY axis going on. Okay, so the length of this one, if I were to count it out, you would notice is 3, and if we're going from 1 to 5, that would actually be 4. So I have 3 as a leg, I have 4 as a leg. My hypotenuse here is my unknown. And so and all you have to do is count that out. So 3 squared is 9, 4 squared is 16, 9 plus 16 is 25. And so now if I undo my square, I've got 5.